this is the example of this morning, and this is how we're going to see this kind of dictionary between combinatorics and algebra. Okay, so here I choose this guy to be my initial triangulation, as in the morning. So I started with that. In the morning, I started with this hexagon, and I decided to triangulate it this way, and then I obtained a quiver, right? So I obtained this quiver. And let's just put the frozen directions also. I will omit the arrows between frozens because, as mentioned earlier, this will be independent of the this would not affect the cluster algebra. So at the end of the day, I have a quiver that looks like this. Right, so I have six frozen vertices, right? And as I tell you, like the periodicities of this quiver and only of the mutation of the mutable part are the same, okay? So what I'm going to do is try to be explicit on this dictionary, but just for the cluster algebra associated to the mutable. For simplicity, I will only work with the cluster algebra associated to the mutable part. I will forget the frozens just for simplicity, because I will just get expressions that look like these ones, but that they are more complicated. Yeah, they will have just more variables, and it will not fit my page like really neatly. So here, as you can see, I decided that this is my initial triangulation. And maybe you cannot see the colors, but this arc, I put it in green, right? I put it in green, and I just put here all the arcs I give a color. This is green, this is red, this is like goldish. This is it's supposed to be purple. This is supposed to be magenta. This is supposed to be yeah, like gold. This is supposed to be orange, so on and so forth. This is a kind of green. So for example, this guy has, this arc appears in all this pentagon in the back, right? So I decided that this is my initial cluster, and this green variable is going to be x1, so it's green. This one is going to be red, it's x2, and this is going to be gold, it's x3, okay? So I should think that the diagonals are corresponding to the cluster variables. So I can identify this green guy with the initial cluster variable x1. So I will label here an x1, just like having in mind having in mind this the cluster complex. Here, as you can see, this face is labeled by x1. It's all the clusters, all the seeds that have a x1 cluster variable. This is x2 in red and correspond to all the arcs that have x2. This is x3, and it's all the seeds that have x3 as a cluster variable. Then here in blue, this cluster variable corresponds to this arc that it's in blue, and yeah, this face corresponds to all of the triangulations that have that given guy. And then I have here like an expression. Here behind, this is the corresponding cluster variable. Here it's like a light green, corresponds to the pentagon behind. In this quadrilateral, this is the corresponding cluster variable, and this is the corresponding cluster variable in the orange part, right? So maybe you cannot see here below, but all the information is already in the cluster complex. I know that this arc, the red one, from going from this kind of hexagons to this kind of hexagons, I just rotate a little bit to the right, so that this vertex corresponds to this vertex. So that's like kind of the thing. So that's why this red arc goes to this red arc. So here I can see the whole information encompassed in a single drawing. So I have like different colors. I mean, like I know that the red arc corresponds to this red cluster variable x2, like this green corresponds to x1, this golden to the x3. So this simplex corresponds to the initial cluster. And then just by colors, you can see which cluster variables are compatible with each other, and so on and so forth. Okay? Now, the idea is to generalize this in a very, provide a far-reaching generalization of this construction. So what we're going to do is the following. The cluster algebra associated to a triangulated surface. Okay? So now we're going to be a little bit like Bruno, and we're going to put our topological glasses instead of our combinatorial glasses. So we don't want to talk about combinatorics, we want to talk about topology. So the idea is to replace this pentagon, well, this polygon by, well, since we now are topologists, this is the same as a disk, right? With a certain number of mark points. Okay? So it's just a surface that is like a disk with mark points. Okay? Now, the diagonals can be replaced by arcs. Okay? And again, the compatibility of diagonals can be stated similarly. So for example, these two diagonals are the same. And well, as a topologist, I would like that I'm able to deform this arc however I want, right? So any other arc that it's a deformation of this, for example, if I move it a little bit more here and I get this arc, should represent roughly the same thing, or should represent the same thing, okay? So this arc can be represented, say, let's put it in some other color. Let's put it in blue. This guy could have been represented by this guy, right? But it could also be represented by, let me just do another figure. That guy, oops, could be represented by this guy, right? Because I'm able to deform things. But now that's a problem because I really want these arcs to be compatible, but then when I'm a topologist, I can start deforming things, and things that look compatible might not look compatible, right? So we're going to do the following. We're going to replace the pentagon, the polygon, replace polygon PR for any surface, for a pair SM, where S, it's a surface, it's an oriented surface, compact surface with or without boundary, and I'm going to replace diagonals and M is a subset of mark points. M is contained in S is a subset of mark points. It's a finite. Is a finite subset of finite mark marked points, Okay, and the important thing is so this replacement and diagonals we replace it by homotopy classes of curves in SM in S that start and finish in a mark point, right? So my object is not going to be a given arc, it's going to be the whole homotopy class. The whole homotopy class, and then compatibility so diagonals, so here these homotopy classes, how I mean, what do I mean? I'm considering we consider continuous maps gamma from the interval, right, to the surface, right? So I go to the surface, right? And maybe you have seen notation. I will ask that the endpoints go to mark points, right? So that's a notation in topology. When you write this kind of symbols, your function goes from here to here, and you ask that this goes to here. Okay? Just like this. So we're going to consider homotopy classes of this, and we say that definition, maybe we assume that the following, we omit the following cases. So we don't want to be contractible. So for example, my surface M, my surface MS, SM, now could be something like this. It could be like a donut. It could have like many holes, and it can have now many connected components. Like this. Maybe I have something like here. This. Maybe I have more like this. And maybe I have something like this. Okay? It could be typically something like this. It could also have empty surface, empty boundary. It could be a sphere, for example. It could be a donut, closed donut. And then I'm considering also mark points inside this guy. So the mark points are going to be in red. This could be a mark point, mark point, mark point. It could have many mark points. It could be in the inside. It could be in the boundary component. I can have many things like this. It could be something like this. It could be a torus with a single mark point. So these are the objects now I'm talking about. Okay? I'm not only talking about polygons, I'm talking about all these kind of objects. So now we have way more things. And the things that I'm going to omit, so what do we want to do? We want to triangulate this. Because we know that if I start a triangulation, it's just going to be a subdivision of this guy into triangles. For example, this is already a triangulation of this. Here I have a triangle. This is a triangle. This is another triangle. And this is another, This is a triangulation. I have like divided into 3 topological triangles, right? And so I know that if I have a triangulation, then I can construct a quiver just using the same construction as before, right? This drawing makes sense in any triangulation. I mean, I was using it in the polygon, but I can use it for any surface that is divided into triangles, okay? So since we want to triangulate, we omit the following cases, like curves let's say this is the boundary of your surface. This is your boundary of your surface. So the surface has mark points in the surface, and the surface is here. I'm going to omit these arcs. These are going to be boundary arcs. They are like, they can be contracted to a boundary segment without points there. So for example, this I don't consider, but this I consider because if I deform it to the boundary, then I have a hole there, like a mark point. This should be things like kind of holes. The mark points, you should think them as holes. So I cannot deform this to the boundary because there's a hole there. Okay? And then this guy should go to a hole, and that's not possible. It's not possible to deform. Whereas if there's no hole here, then I can deform it and make it a boundary segment. Since I want to triangulate, I don't want it to be contractible neither. So this is bad. If this is my surface and this is like the boundary, I don't want to be contractible. I don't want to be contractible. This is bad because this constructs to a point and then I'm not triangulating anything. And also if I have like an interior point, I don't want to be contractible. So here it's, let's say this is empty, this is contractible, right? But what we can actually allow are arcs that look like this that are not contractible, that are essential, okay? So we omit these kind of cases in which, I really, like, I'm not really using these arcs to produce triangulations. At the end of the day, we want to cut out a surface into triangles. These kind of things will not help. So we just throw them away. And then we have to talk about compatibility. We say like 2 arcs are compatible. Definition. Gamma 1 and gamma 2 are compatible if there exist representatives in the homotopy class of gamma. This guy here denotes the homotopy class. This is homotopy class. Homotopy class. In the homotopy class of gamma 1 and the homotopy class of gamma 2, such that do not intersect in their interiors. So now, for example, these are compatible. These 2 are compatible because I can deform. What this condition is telling you is I can deform them so that they don't intersect. Okay? And finally, maybe I will put it here. Definition. A triangulation of a surface SM is a maximal collection of compatible arcs. Okay? So for example, I'm recovering the notion of triangulation of the polygon by taking this generalizations, okay? Now, for example, if I work topologically and I follow these definitions, a triangulation of the polygon, it's the same as the one I gave before. Okay, compatible arcs are going to correspond to compatible diagonals, and a triangulation of the polygon by diagonals is the same as a triangulation by these arcs in a topological sense. Okay? Now, the rest just generalizes. Given a almost generalizes. Questions so far? Is it clear for everyone, the construction? Yes? Okay. So the name of the game, it's give a surface and divide it into triangles. That's it. That's the name of the game. That's what we're doing. But there are pathologies. In the polygon, there are no pathologies because all the triangles have different sides. But now we're able to deform things, so there are going to be pathologies. So let me just put it here, like example of pathologies. Pathologies. For example, what about this? This is my surface. It's a disk with a mark point in the interior and a mark point in the boundary. Okay? That's my disk. That's my surface. So now I want to triangulate it. Well, is this a valid arc? This is a valid arc? Yes, it's not forbidden. It's not among the forbidden ones. And is this a valid arc? Well, it's not because it kind of it can be deformed to the boundary, right? So let's just put here another point so that it's a valid arc, right? Now here I have triangles. I have two triangles. I have this triangle and this other triangle. What's the problem? They don't look like triangles, right? They are like degenerate triangles, right? One of the triangles looks like this, right? And the other one it's a little bit better because the three sides are different. And the other one looks like this, right? So it has three sides. This guy has three sides, but two vertices, and this has two vertices and two sides, somehow. Okay? Now I have a problem because the drawing I want to use to construct my recipe, I really want this to be my recipe to construct a quiver. Okay? That's what I want. But then it might not be possible, right? With this recipe, well, I can think that this is a vertex, that this is a vertex. For a moment, I will just pretend that these are different sides. Let's just play the game. Let's just imagine that they are different, and let's see what will happen. So here I have a triangle, and then if I will have like this picture, but a little bit like degenerate. But I will have to have this kind of disoriented guy. So let me be a little bit more. Maybe let me just make it a little bit more exaggerated so that one can see what's going on. Okay? Now, let's say this is vertex 1, this is vertex 2. And this is vertex 2 as well. I mean, this should be vertex 2, but now I remember, okay, don't be fooled. You were just pretending that they were different, but they are not different. They are the same. So they should be called the same, right? So what I will have is 1 and 2, and what I will have it's exactly the kind of things I don't want to see. I'm seeing exactly a 2-cycle and a loop. So this is a pathology. Okay? This is problematic. This is problematic because we really don't want to see this, and my theory so far only works if I don't see these configurations. Okay? So what do we do? What would you do? Run away. Like forget about the problem. No, we're mathematicians. We try to find solutions, right? So there are 2 solutions, right? What would be the first solution? At least there are 2 possible solutions. Tell me one. I cannot listen.
Can you please repeat the question again?
Okay. We kind of feel that we're in the right direction. That if we start triangulating surfaces, we can produce quivers. And also, you can kind of imagine that a surface with a finite number of points can be triangulated with a finite number of arrows, of arcs. So I would consider like finite quivers if I'm replacing arcs by vertices. And so what's the aim? Is to construct a quiver, to have a surface, divide it into triangles, and construct a quiver. Okay? That's kind of the aim. It's going to be really, really a good aim because actually we're going to classify all quivers of finite mutation type using this procedure. So believe me, it really makes sense to follow this. So the question is, I face pathologies, this kind of pathologies. How do I solve the pathologies? That's the question. How do I solve the pathologies? We leave them. We don't consider them, right? Something like this, did you say? Deform it? Deform it. Okay, that seems a little bit, you want to deform the surface, but we were not doing that in the polygon case. In the polygon was fixed. So we want that the polygon case kind of remains like as the intuitive example, okay? So maybe deforming, we don't want to change the surface. We really don't want to change the surface. We want to keep it. So, well, maybe first solution is consider surfaces or consider triangulations that do not have this kind of triangles, that have triangles that all look like good. That would be a solution. Just consider maybe not all the triangulations of a surface. Consider a surface that has triangulations without degenerate triangles. Actually, we will call this self-folded triangles. This is a self-folded triangle. Self-folded triangle. So we want to consider surfaces that admit triangulations without self-folded triangles. If I don't see self-folded triangles, then I only see triangles like this, and then I can consider a quiver, and then we're going in the right direction. Okay? What's the problem? There might be surfaces whose all triangulations have self-folded triangles. For example, this guy, the digon with one mark point. Not any. This is a triangulation without self-folded triangles. Okay? So we can do that. We can just throw away the surfaces that do not have Now the second problem is more complicated. If we really want to mutate, we want to do mutation in any arc. So let me show you a picture. Oh. Let me just maybe do some preparation. Let's just consider this example. So for example, if I want to construct a quiver from this, using this recipe, what I would have is 4 vertices, this vertex, and this frozen vertex, and this frozen vertex. Okay? Then I will have something like this, like this, like this, and then I will have something like this, like this, like this. Okay? So at the end of the day, what I get is something not too satisfying, but not too bad, because it looks like I have an arrow here, I have an arrow there, and I have an arrow, blah, 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 other way around. I have an arrow here, I have an arrow there, and I have this. So again, it doesn't look nice, because I have these 2 cycles. Yeah? I have also a 2 cycle. But I can say, okay, in my mutation algorithm, when I have 2 cycles, I simply erase them, right? So maybe I can just erase these 2 guys and then get this quiver, right? And I know that the quiver, you know, the periodicities of the cluster algebra will only depend on the mutable part. So here I get something of type A1 cross A1, right? So then let me show you a picture that will be more will show more clearly what I want to communicate. Okay, so here you can see precisely the example I have. Here I have a triangulation of this diagon with a marked point in the middle, and then this triangulation is kind of fine. These 2 are kind of bad. Right? So I can start for something that looks good, type A1, type A1, and then I get to problems. I get triangulations that have like these pathologies, and also they cannot, you know, maybe I do it here. This top arc, I can flip it. This top arc, I can also flip it. But here, I can only flip one. I cannot flip the interior one. I only can flip the exterior one. If I flip the exterior one, I go back here. If I flip the lower one, I get here. And here, I cannot flip this arc that is in the middle. I can only flip the exterior one, right? So I cannot mutate in every possible direction, okay? So there are 2 solutions. Consider surfaces that do not have these pathologies. And the second, that is more complicated, is if I see pathologies, create a way to solve them. And this is meant to be the picture here. So this is like so in the theory, people introduce other kind of arcs that have this mark, this kind of bow tie. You know, they have like this marking, and they use, you know, they really change this definition so that they can consider also arcs with taggings, and it's kind of technical, and I don't want to elaborate on that. Okay? But there's a possibility. I mean, these pictures are meant to be showing that you know, like I can replace like self-folded triangles by some combinatorics. Okay? I don't want to elaborate on that because it's technical, it takes time, and we're going to miss the point. So what I want to reach is the main point of this. It's the following theorem. So suppose T is a triangulation of Sm such that T has no self-folded triangles. Then we can define a quiver Qt as in the case as before. Yeah, just like by this drawing, like using this kind of drawing. Okay? And the theorem that I'm going to put it in what I'm going to put it in quotes, because I'm not going to, I don't want to spend many times in the technicalities. I just want to communicate the ideas, like that you get the feeling of what's the content of the theorem. It's that quivers of finite mutation type theorem 1, every such Qt is of finite mutation type. So it's very nice. Now I have a way. Do you remember at the beginning I told you, like in the first lectures, like there are very easy questions to pose. You can ask, I define quiver mutation, and then you can ask, when do I produce a finite number of quivers? Okay? Just draw a surface that has like a nice triangulation, and that quiver is going to be of finite mutation type. And the idea is the following. It's like, a surface has only a finite number of triangulations. That's kind of the core idea. A surface only has a finite number of triangulations. So what I really want to happen is that the flips of diagonals corresponds to mutation. This is going to happen. And then the fact that I have something of finite mutation type, it's because a surface only has a finite number of triangulations. So that's the idea behind this theorem. Okay? Just like the polygon. The polygon has a finite number of triangulations. I cannot find an infinite number of different triangulations of a polygon just with its diagonals. It's not possible. Everything is finite. Right? So it's the same for surfaces. And the second part of the theorem, up to exceptions, these are all the quivers of finite mutation type. Of finite mutation type. Of finite mutation type. And the exceptions are going to be quivers with 2 vertices and many arrows. Quivers, these exceptions are quivers with 2 arrows and are with 2 vertices, arrows, and are greater or equal to 3. So these quivers cannot be produced using a surface. And there's also like an explicit list. Maybe I just let, I don't know where I put this. There it is. I think I didn't put the list of exceptions. I wanted to put it here. But there are a list of, maybe just go to here, quivers of finite mutation type. And you will find this images. Okay. None of this. Okay. Okay. Shapiro, Felixson, to Markin. Okay. This is the paper where they show this classification, and I really want to show you the picture of the exceptions. These are the exceptions. So there are 11 exceptions. These, for example, E6, E7, E8 are of finite mutation type, are of finite type. In particular, they are of finite mutation type. But they cannot be obtained by a triangulation of a surface. You cannot construct a surface such that this is like the mutable part of the triangulation. And also these other quivers that you here see. All of them are related to E's, and these you have like two sporadic examples, X6 and X7, so there are exceptions. So these are the exceptions, and these are the exceptions. Any other quiver of finite mutation type comes from a surface, okay? The theorem is like that, I'm sorry. It's like, it would be beautiful that it's just by topological surfaces, but there are exceptions, not big deal. This happens. And I just want to finish by saying that, that maybe point 3, it's like there's a dictionary between arcs and cluster variables, triangulations and seeds, and mutations and flip. So just to finish the talk, the lecture, let me show you this. So here, I'm representing my surface is an annulus or a cylinder. It's a cylinder. So the cylinder or the annulus has two boundary components, right? One circle and another circle. So you can see here in the exterior circle is one boundary component, and the interior circle it's another boundary component. So this you can think it either of a cylinder or an annulus, okay? One of the components has one mark point, and the other two components, and the other components has two mark points. And here I have the graph of triangulations. Well, I'm sorry, below, yeah. Here actually I have the complex of arcs. The complex of arcs, if you can see, the vertices of this complex, okay, I'm going to use this, just to finish. This is a simplicial complex whose vertices are the arcs. So here, this arc corresponds to this vertex, this arc corresponds to this vertex, this arc corresponds to this vertex, so on and so forth. And as you can see, the homotopies we are considering should leave the boundary fixed. That's why, for example, this guy, this arc, and let me see. Well, let me just put a drawing here. Just something that I forgot to mention in my definition of arc is that the homotopies should leave the boundary fixed. Okay? So for example, this arc, and this arc are not the same. Even though I can just topologically take like this cylinder and just like turn it. You know, imagine this is clay. If I turn it, I go back to this, right? Those are the homotopies I want to forbid. I want to just keep the boundary frozen. So the boundary is frozen just as the vertices. So that's why I still have like these arcs that they start wrapping around. So I have here a complex where, you know, like vertices correspond to arcs, edges to compatible, and faces to triangulations. So as you can see here, I can see the triangulations, right? So these would correspond to the cluster complex associated to the quiver associated to any triangulation of this, and this would be the exchange graph. Here, as you can see, vertices. This vertex, for example, is the triangulation formed by this arc, and this arc. Okay, so here you can see like a graph, which looks like which should be considered as the exchange graph, and this simplicial complex that should be thought of as the cluster complex. So let me just compute the quiver of any of this annulus. So let's just pick a triangulation. What about this one? Okay, I'm just going to pick that triangulation. So it goes like this, like this, like this, like this, and like this. Is this the triangulation I picked? Yes. Okay. Now I'm going to compute the quiver. So I should have this guy, and this guy. And now I have to look at the triangles. I will also put the frozen information, just right, to have it clear. So I see a triangle here. So this is empty. This is like empty. And here I see a triangle, right? Here I see a triangle. Okay? And here I see a triangle. And they are all the triangles I can see. Okay? So what's the quiver I obtained? I obtained something that looks, let me just put maybe 1, 2, 3. So let's just put it like this. 1, 2, 3. So I have one arrow from 1 to 2. I have an arrow from 2 to 3. I have an arrow from 3 to 1. No, from 1 to 3. Okay? And then I have frozens. But I will forget about the frozens. Okay? I can put them. I can put them if you want. Let's call them 4, 5, and 6. Okay? So let's just do 5, 4, 5, and 6. So 4, it has an arrow from 3 and has an arrow to 1. 6 has an arrow from 1 and an arrow to 2. And 5 has an arrow from 3 and an arrow to 2. Okay? So this is the quiver. Okay? So all the mutations of this quiver would appear in the vertices of this graph. Right? So you will see an infinite collection of quivers. But the quiver itself, now it's independent I mean, now if I just, make this arc simple, the quiver will look the same. Just like here. I mean, like, even if I have so many arcs, at the end of the day, if I allow now myself again to go back to the boundary, I can start like, like this, making these arcs that wrap around. I can make them simpler. And I only have a finite number of triangulations, actually. So even if even if the cluster algebra is of infinite mutation type, the quiver is of finite mutation type, because the drawings itself will only depend on the topology of the surface, whereas the cluster structure will depend on the surface. The topology of the surface when I fixed the boundary, when I freeze the boundary, okay? So I hope, I'm going to stop here. I just hope that you get, I mean, from these pictures and this discussion, you can get an idea of you know, this theorem. And maybe the very, very last remark, it's that just like in the case of the polygon, we know that there was an algebraic variety sitting in the background, which was the Grassmannian. Here, there's also an algebraic variety sitting in the background. But it's way more complicated to describe. It's related to representations of the fundamental group of the surface in the special linear group. And it's actually related to something called Teichmüller theory in hyperbolic geometry. So it's a moduli space. It's a moduli space. So you need algebraic geometry to describe like the variety sitting on the background, but it's like a variety that is important in mathematical physics. So as you can see, this looks like, you know, like the pictures that people will draw in string theory, where the boundary of the surface are strings, and how they start moving represent how strings move and interact with each other. Okay? So this is actually also related to string theory. So yeah, it's a beautiful story, but I'm not going to explain. I just want you to have a little bit of the feeling of what's the connection behind. Okay, thank you.